Okay, I'm going to talk to the key at this point. And the first thing I noticed is that they wrote down the integrand, which is the natural log of 1 plus x cubed, and it's differentiated. How do you differentiate the natural log? Let's write this over here, dy dx. That's going to be 1 over its argument, which is 1 plus x cubed times 3x squared. I clearly see that written over here. The next thing I want to point out is noticing things. And the reason for differentiating is so it looks like something that's more familiar to me. All right, now, when I say more familiar, I'm talking about that quotient, all right? Now, not the 3x squared, but I'm looking at something that looks sort of like this over here. Now, I should recognize this as being 1 plus u squared plus u cubed plus yada, yada, yada. I don't really see that, though. What I see is 1 over 1 plus x cubed. And I need to write that a little bit differently. I need to write that as 1 over 1 minus x being cubed. And then I'm going to pop it in over here. And what would that give you? 1 minus x cubed plus x6 minus x9, yada, yada, yada. Let me show you where that's written. That's written over here. 1 minus x cubed plus x6 minus x9, yada, yada, yada. But what are we doing? We're multiplying it by 3x squared, all right? Let me get my eraser out. I'm pretty comfortable I got there. But again, if it's a long road, you may forget why you've gotten there. And all I did was I wrote a derivative down of this guy over here, and I'm pretty comfortable if I multiply through on this, I'll get something like this over here. Then the question comes is you need to integrate that guy, all right? Now, why is that? What are you trying to do is you're trying to get back to that natural log problem, all right? So let me point out what we're trying to do. We're trying to integrate these terms over here. Let me put this down for you. So the natural log of 1 plus x cubed dx, well, not dx, I'm sorry. Let me write this over here. We just differentiate that, and we're going to integrate it to go backwards. So we know this guy's derivative, and now we're going backwards by doing the antiderivative. So I integrate it, and it'll get me back to the log of 1 plus x cubed. Is this easy to integrate? It is. Now, what I mean by easy to integrate, that infinite series is easy to integrate. It has a nice pattern to it, all right? So let me go through that. I'm looking at that, one step at a time. So the natural log of 1 plus x cubed, there's going to be some constant integration. And then, whoops, sorry about that. The antiderivative of this term over here, increase it by 1 divided by 3. That's not so bad. Increase this by 1 divided by 3. That's not so bad. Increase that by 1 divided by 3. And again, not so bad. So it looks like pretty good, all right? Now, someone says, I wonder what the C is. And I often wonder about that, too. Can I figure it out? So I can figure it out by selecting a very easy x value. So the x value I choose, I would probably choose 0. And the reason for that, the natural log of 1 is incredibly easy to do. But more importantly, on the right-hand side, every single term disappears except for C. What do I know C is now? I know C is 0. All right? So where do we get to? We got to this stage over here. We know now this is equal to this over here. But the bottom line is I really didn't want to know just that. What I wanted to know was what the integration of that is. So I write it down, and I integrate both sides now. Let me repeat this. I still don't know what this is, but I certainly can integrate this business over here. How do I do that? One term at a time. There will still be a constant of integration. Term-wise, antiderivatives, x to the 4. I'm going to write this in, some people say a peculiar way. I'm going to put the 4 there. x7, I see the 2 there, I see the 2, 7. x10, 10, 3 was already there, x13, so forth and so on. And by the way, it is alternating. All right? So what I'm doing now, I'm going to write down the sum. All right? The C is there, but the sum, whoops, sorry about that, not equal, plus the sum, I'm going to start at 1. I'm going to go off to infinity. Let me get my eraser out. And as I do this over here, I want to point out what we're looking at. We're only looking at one thing at a time. I want to do this first, though. And so what do you mean first? I want to do the 1 first. 1, 2, 3, 4. So I'm going to say that looks like a really easy pattern to me. It's just going to be n over here. I get 1, 2, 3, 4. There will be a multiplier, all right? The next thing I want to do is I want to do the alternating pattern. I see plus, I see minus, I see plus, I see minus. So I'm going to say it looks like -1. Let's be careful that the first term is positive, so it's going to be n plus 1. So I would get a square, which is positive. I think it's negative. Yeah, it looks pretty good, all right? So I'm going to go the next to the, this x to the power thing, all right? So it's the 4th power, and I know it's going up by 3, right? I know that much. It's going up by 3, up by 3, up by 3. So it has something to do with 3n. So write this over here, x to the 3n. But if I started at 1, I'd have 3 there, so I need to add 1 to it because I need a 4, right? Does that, if I go to 2, what do I get? I get 6 plus 1 is 7. Yeah, it looks like it's pretty good. What's the thing on the bottom? It's a power, which is 3n plus 1. All right, I think I got my series down. I'll just point this out to you over here. I got the C. I'm not understanding what the C is at this point, but I'm seeing this over here. I'm getting the same series, all right? Now, by the way, they said determine a power series. I did determine a power series, by the way. However, I will say it's polite if you could write down the interval and radius of convergence. I will say this, though. Looking at it, I have a good idea that I got this from the geometric. I know the geometric series for this one over here that I just did over here, that the x would be between plus or minus 1. I know that much, right? What I'm not clear about is I wonder if I should include those endpoints. With integration, you might gain an endpoint. So let's test it out and see what happens. If I did that, I'm going to write it down for you. I'm going to test out the 1 first, and this is the series I'm testing it out in. What's going to be n equals 1 to infinity. And if x is equal to 1, well, that couldn't get any easier. You just get -1 to the n plus 1 over n, 3n plus 1. That's definitely a convergent alternating series. All right, it's also absolutely convergent, by the way. Let's do the -1 though. Put it over here. And what do you get there? N equals 1 to infinity. And gee, if I put -1 there, what do you get? Let's write this down inside. You get -1 to the n plus 1 times -1 to the 3n plus 1. And that would be -1. I add the powers together. That's 4n plus 2. That's always positive, by the way. All right, even powers. What do you get in bottom? N and 3n plus 1. By the way, it's also a convergent series. Just make a comparison with the p series and you'll get that. All right, so I got that. And I'm pretty comfortable now that I can write down the interval. The interval I is going to go from -1 to 1. And the radius for this over here is going to be 1. All right, this is going to be the final answer in this problem over here. Again, finding the C might be a little more difficult, but the bottom line, I think we're okay. Thank you.